Okay, in lesson 3, we're going to talk about imaginary numbers. It says that I can define and use the imaginary unit I. Before we get to I, or the imaginary numbers, let's do this warm-up. Okay, we want to simplify this expression. We want to make sure we're using the correct order of operations. I'm going to use PEMDAS to help me. We always do parentheses first, then exponents, multiply, divide, add, and then finally subtract. Okay, multiply, divide, add, and subtract, those steps are interchangeable. All right, so we're going to worry about simplifying what's inside the parentheses first. These are not like terms, so they cannot be simplified. Okay, so then I look at exponents. Really, there's no exponents in this problem. Multiply, divide. Well, I can multiply the 4 through, and I can multiply the 6 through. So we're going to get 4x minus 4 plus 6x plus 36. So that's done. I don't see any division. And then add and subtract. So now we're going to combine like terms, essentially. What is a like term with 4x? Well, I'm looking for another term that has x in it. 6x has x to the first power in it. Add those together to get 10x. Then we have negative 4 and plus 36. Those are like terms because they're both constants. So we get 10x plus 32. For the next warm-up problem, we're going to list all perfect squares for numbers 1 through 13. So over here, I'm just going to label the left-hand column with the numbers 1 through 13. Okay, and what does it mean to be a perfect square? Well, we can find a perfect square just by multiplying that number by itself. So if I think about multiplying 1 by itself, we would have 1 times 1, which is 1. Another way we could think about it is doing 1 squared. That's why it's called a perfect square. Same thing with 2. If I want the perfect square of it, we could just multiply 2 by itself. Instead of multiplying 2 by itself, we could also square it and get 4. So that's why it's called a perfect square. Okay, again, 3, if I want its perfect square, we could multiply it by itself or square it to get 9. 4, to get its perfect square, we'd square it to get 16, right? 4 times 4 is 16. 5 squared is 25. 6 squared is 36. 7 squared is 49. 8 squared is 64. 9 squared is 81. 10 squared would be 100. 11 squared is 121. 12 squared is 144. And then 13 squared is 169. Okay, so that's our list of perfect squares for the numbers 1 through 13. So I might even write up here at the top, perfect squares. Okay, the opposite of squaring something is square rooting it. So for example, if I wanted the square root of 16, I'd get 4. If I wanted the square root of 36, I'd get 6. Those are inverse operations. And it's nice when I'm given something perfect under a square root. Sometimes I'm not going to be given something perfect under a square root. Okay, for this unit, you need to remember how to simplify radicals. So if I'm not given something perfect, like 18 is not a perfect square, how would I simplify it? Well, first of all, I know 18 is not a perfect square because it is not in our list of perfect squares. See how 18 is not in that list? So what do? Well, 18 is going to fit in between 16 and 25 over here. I need to figure out the largest perfect square that 18 is divisible by. Is 18 divisible by 16? No. Is 18 divisible by 9? Yes. So I can actually break 18 into 9 times some other number. What is that? 9 times 2 is 18, where 9 is the perfect square, right? Square root of 9 times square root of 2. Because 9 is perfect, I can simplify that. What's 9 the perfect square of? 3, right? If I look over here to the right-hand side, we can see that 9 is a perfect square of 3. So I'd simplify this root. Anything perfect can leave that radical, and then the 2 is not perfect, so it has to stay at home under the radical. kind of a sad story, right? If you're perfect, you get to have it leave the house, right? But 2 is not a perfect number, not a perfect square, so it has to stay at home under the radical. Let's do the same thing with 72. Is 72 a perfect square? Look in your list of perfect squares. Do you see 72? No. So where would 72 fall? 72 would fall between 64 and 81. Okay, let's figure out what the largest perfect square is that 72 is divisible by. Is it divisible by 64? No. Is 72 divisible by 49? No. How about 36? That might work. Let's type it into our calculator. 36 does work. 36 times what would give me 72? 36 times 2, where 36 is perfect. Let's break that into a product where we have a perfect square under the square root, and then we have 2, which is not perfect, under the square root. Okay, let's simplify the square root of 36. What is 36 a perfect square of? 6. So I can simplify this because it's perfect. It's going to leave the root, and then 2 is not perfect, so it has to stay at home underneath the radical. All right, and that's how we simplify square roots. Now, what you're going to notice is that both of those examples had positive numbers under the radical, right? Like when we look at this, we had 72 or 18 under the radical, and both of those were positive numbers. That's not always going to happen. Sometimes we'll have a negative number under the radical, maybe like -4. And in that case, you would have no real solution. Mathematicians did not like that. They didn't like the fact that there was no real solution, which is why they made up the imaginary numbers. So let's look at our definition of imaginary numbers. It says imaginary numbers were invented so that negative numbers would have square roots. Mathematicians wanted it so that all equations would be solvable and have solutions. When a graph doesn't cross the x-axis, we say that the solutions are imaginary. Okay, so if I have a graph, let me go ahead and draw this graph in. Maybe something that looks like this. It's possible that that graph has imaginary solutions. See how it does not cross the x-axis? Okay, then we would say that the solutions would be imaginary. If we had real solutions, we would see those real solutions as x-intercepts. So like here, this would be imaginary solutions. I just abbreviated it, imag. Versus if I had something that looks like this, okay, the solutions would be right here and right here where it crossed the x-intercept. So it says not all quadratic equations have real number solutions. For example, x squared equals -3 has no real number solution or solutions because the square of any real number is never a negative number. If I were to give you this problem, x squared equals -3, and I ask you, what number can you square and get -3? What would your answer be? You can't, because what happens when you square a number? What happens to the sign of it? You square it and it becomes positive, right? So if you square a number and it becomes positive, are you ever going to get -3 as your output? No. Okay? So the idea is that there is no, bless you, no real number solution. Okay? That doesn't mean that there's no solution. We're going to talk about how you would have an imaginary solution for an example like this. Okay? So to overcome the problem of not having a real solution, mathematicians created an expanded system of numbers using the imaginary unit I. And they defined I to be the square root of -1. That's what I is. Okay. So let me ask you a question. If I is the square root of -1, then what is I squared? -1. Very good. If I square both sides of the equal sign, we get that I squared is, well look, squaring a square root. These are inverse operations. So just leave us with -1. See how naturally I squared is -1? Okay. that's what it notes over here. Note that I squared is negative 1. The imaginary unit I can be used to write the square root of any negative number. Okay, so what is I? Someone tell me. I equals, great, square root of negative 1. Okay? Therefore, I squared is what? Tyler, what's I squared? Negative 1. Okay? So that's what I want you to memorize. I want you to memorize that I is the square root of negative 1, and I squared is negative 1. These are properties that you need to memorize. Okay. All right. So here's our core concept. It says if r is a positive real number, then the square root of negative r is equal to I square root of r. Well, that makes sense because I can break the square root of negative r down into the square root of negative 1 times the square root of r. Does everyone agree that the square root of negative r can be broken down that way? What is the square root of negative 1? Madeline, what's the square root of negative 1? Huh? It's I. Yeah, exactly. It's I. So we can replace that with I, it's just a substitution, and get I radical r. See how that's what it's equal to? Because it's equal to I square root r? That's exactly what we got. Okay. An example with constants would be right here. See how they're finding the square root of negative 3? And they say that the solution is I square root of 3. Anytime you have a negative underneath the square root sign, all I want you to do is put an I out front and get rid of the negative under the square root sign. Okay, and you can do that because I is the square root of negative 1. That's why it works. Okay. Says by the first property, it follows that I square root of r, quantity squared, is negative r. Again, this is something that you can actually prove yourself. If I want to square I radical r, I have to square both parts. I have to square the I, and I have to square the square root of r. Okay? Square I, and square the square root of r. I'm squaring both parts. What is I squared? And what's I squared? Negative 1. Okay. And then what is the square root of r squared? Well, the square root and squared are inverse operations. One of them does the other, and it leaves me with r. So see how negative 1 times r would give you negative r? Okay, so there you go. That proves it. Okay, so that's what they do over here. See how they have I radical 3 quantity squared? They square the I, and they square the square root. We have I squared times 3. I squared is negative 1. So we get negative 3. Okay? Whenever you have I squared, what are you going to replace it with? What is I squared?
Negative 1.
Negative 1. Do not leave it as I squared. You have to simplify it down to negative 1. Okay? Don't leave I squared. Okay. So let me ask you a question, boys. You're walking down the hall, you see a cute girl, right? What is the first thing you notice about the cute girl? Her beautiful eyes, right? That's always the first thing you notice about a cute girl. If it's not, that's what you should look at, right, ladies? That's what you should be looking at. So, if you walk up to this math problem, it works the same way. What is the first thing you should look at in the math problem? It's beautiful eyes. Yeah, okay. So, that's the first thing I want you to look for. Does it have an eye? Okay. I look at this guy. It's a square root with a negative underneath the radical. Are you ever going to take the square root of a negative number and get a real solution? No. So as soon as I see that negative, I know that I'm going to replace it with an I out front, right? This is really the square root of negative 1 times the square root of 25. See how I just broke negative 1 and 25 apart? Okay, so what is the square root of negative 1? I. So see how every time you see a negative underneath the radical, you can just replace it with an I out front. Now, that looks a little bit nicer. What is the square root of 25? It's 5. Okay, so I have I times 5, which would be 5I, and I'm done. That's my answer. So in part B, I walked up to this math problem. The first thing I look for is, are there going to be any i's? Okay. Because I'm taking the square root of a negative number, I know that there are. I'm going to take an I out front. I'm going to get rid of the negative underneath the square root. I radical 72. Now, is 72 a perfect square? It is not, okay? So what I want to do is find the largest perfect square that 72 would be divisible by. What is 72 divisible by? 1 and 72, 2 and, I'm going to divide it by 2. Say it loud. 36, that's correct, yeah. 3 and, what is that? Someone type that in. 72 divided by 3. So I have 24. Thank you. Okay, is 72 divisible by 4? 18. I don't think it's divisible by 5, right? What about 6? 6 and 12. Is there anything else? 8. 8 and 9. Okay, so I ran out of room. Okay, so 8 and 9. So let's think about which of the factors of 72 are perfect squares. 1, 4, what else? 36. Yep, 9. Okay, so I identify all the perfect squares. I want to choose the largest perfect square that 72 is divisible by. So 36 would be the largest perfect square. Okay, so I'm going to do I times the square root of 36 times, what is that? 36 times what? 72. So 36 and 2 gives me 72. See how I took 72 and I broke it into 36 times 2? I strategically chose 36 because I can take the square root of it. What is the square root of 36? 6. See how 36 is perfect? Okay, so I have I times 6. I took the square root of that. Can I take the square root of 2? No, that was the leftover part. Okay. Whatever comes out of the square root, you want to multiply. Okay, so see how it's multiplied by 6? Okay, so I have 6I square root of 2. That's how that works. All right, part C. Instantly, as soon as I look at part C, I see that negative underneath the square root. That's no good. So I'm instantly going to pull out an I, and then the 9 under the radical will be positive. Can I take the square root of 9? Is 9 perfect? Yeah, what's 9 a perfect square of? 3. Okay, so that whole thing can be reduced down to 3. So I get negative 15I. There we go. Any questions? Okay. I want you guys to try this guy, number 2. You guys try number 2. So instantly, as soon as I see the negative square, or the square root of negative 1, as soon as I see square root of negative 1, I replace it with I. Okay? Is 12 perfect? No. Okay, so I need the largest perfect square that 12 would be divisible by. What are the factors of 12? 1 and 12. Yep, 2 and 6. 3 and 4. Right? These are all the factors of 12. Right? 12 is divisible by all of those numbers. What is the largest perfect square that 12 is divisible by? Well, the only perfect squares are 1 and 4 here, right? So it would be 4. So I'm going to break this guy down into 4 times 3 is 12, right? Where 4 is perfect. So what is the square root of 4? 2. Can I take the square root of 3? No. Okay, so it's going to stay at home. If it's not perfect, it has to stay at home under the radical. You only get to leave the house if you're perfect. Isn't that so sad? Okay, so we get 2i square root of 3. That's the idea. Okay, so what I want to do now is just kind of look at patterns for I. It says write each expression below in terms of I. We're just going to say that I is I, right? And what is I squared? -1, right? So those are the givens. And I want you to simplify the rest of these based on that knowledge. So like I cubed, for example, I could break that into I squared times I to the first. Do you agree? Can you pull that apart? What is I squared? -1. This is really -1 times I, or negative I. So let's just call I cubed negative I. And using that same idea, let's do it with I to the 4th. What could I break I to the 4th down into? I squared times I squared. Sure. Which I squared is just -1, right? So -1 times -1. What is the value of I to the 4th? Just 1, right? -1 times -1 is just 1. So what we're doing is we're just going to keep doing this, breaking apart the I to whatever power it is to try to simplify it. This is really helpful. If I can reduce something to 1, that's what I want, right? That's the most desirable simplification. So here, when I'm looking at I to the 5th, you could do I squared and I cubed, but that's not going to help you simplify it to 1. I would rather do I to the 4th times I to the 1st, right? Anytime you can use I to the 4th, use it. Because what does I to the 4th simplify to? 1, right? This is really 1 times I. 1 times I is just I. How can I break I to the 6th down using I to the 4th? That would be I to the 4th times I to what power? The 2nd, right? Which, what is I to the 4th? 1. What's I to the 2nd? -1. What's 1 times -1? -1. Anybody notice something interesting that's happening? Oh, what do you think I to the 7th is going to be? Oh, maybe. Let's see. I to the 4th times I to what power is I to the 7th? The 3rd, right? What's I to the 4th? 1. What's I cubed? -I. 1 times -I. Look at that, -I. Okay, what do you think I to the 8th is going to be? 1, right? It's really just I to the 4th times I to the 4th, which is 1 times 1. Okay, so we get that I to the 8th is just 1. Okay, so you can see a pattern emerging. I bet this is going to be I bet this is going to be -1, I bet this is going to be -I, and I bet that's going to be +1, right? This is called cyclic if it keeps having the same answers, the pattern. Right, it says any power of I is going to be one of these 4 answers. So actually there's a rule that you could use. Since we know the answer is either going to be 1i, -1, or -I, you can look at the remainder to help you. If the remainder is 0, then the answer is 1. So like here, if I take the exponent and I divide by those 4 options, see how it comes out as 2 with a remainder of 0? Okay, that's when it's going to simplify down to 1. Or here, if I have 12 and I divide by 4, see how that divides out evenly? We get 3. Right? There's no remainder. You get 1. Okay, anytime there's no remainder, you get 1. Look at this guy. Like I to the 7th. If I take the power 7 and I divide it by 4, what do I get? How many times does 4 go into 7? Once, so that gives me up to 4. And then 5, 6, 7, I have a remainder of 3, right? 1 3/4, where I have a remainder of 3. What happens if the remainder is 3? My answer is negative I. Isn't that what I got? Negative I? Take 11 and divide it by 4. How many times does 4 go into 11? Twice. That's 8. 9, 10, 11. See how, again, my remainder is 3. Okay? You get negative I. Okay? If the remainder is 2, then that's when I'm going to get negative 1. So see how here I do 6 divided by my 4 options. 4 goes into 6 one time. That gets me up to 4. And I have 5, 6. That's the remainder of 2. Right? So my answer is negative 1. Here, if I take 10 and I divide it by 4, how many times does 4 go into 10? Twice, right? That gets me up to 8. And I have 9, 10. Remainder of 2. Okay. That gets me negative 1. Okay. And the same thing goes for if the remainder is 1, then I would get I. Right? 5 divided by 4, you get 1 and 1/4. See how the remainder is 1? Okay, so if you like the rule, you can use it. Or if you just like to break it into I to the 4th, that's fine too. Okay, so whatever works for you. The very last thing we're going to talk about today is what is a complex number. A complex number in standard form is A plus BI, where A is the real number part. Oh no, my thing froze. A is the real number part, and BI is the imaginary part. Okay, so let me go ahead and just get a new screen up here. All right, here's my new smartboard. Okay. Let's see. Okay, so you have a real part and you have an imaginary part. Okay? So the real part is going to be your A value, and then the imaginary part is going to be your BI. Okay, so this is your real part, and this is your imaginary part. Okay, and I know it's imaginary because it's got an I in it. It says two complex numbers are equal if and only if the real parts are the same, A equals C, and the imaginary parts are the same, or B equals C. That actually makes sense, because if I give you, like, let's say 2 plus 3i equals 2 plus 3i, is that a true statement? Yeah, right? Why is that a true statement? Well, it's because the real parts are the same, and the imaginary coefficients are the same. So it makes it equal. Okay. What happens if I give you 5 plus 3i equals 4 minus 2i? Is that true? No, it's not true. Okay, the reason why is because the real parts are different and the imaginary parts are different. It does not make a true statement. Okay? You want your A and B value to be the same on both sides. Okay? You want it to be the same complex number. When we're talking about complex numbers, this is a broad umbrella term. Complex numbers actually include the real number system and the imaginary number system. Okay? It's just with real numbers, my I term is 0. Okay? Plus 0i. Well, that leaves you with a real number. Where an imaginary number is going to have this imaginary component I in it. So here's what I do. Okay? It says find the values of x and y that satisfy the equation. You go ahead and erase all of this good stuff. When are two complex numbers going to be the same? they're going to be the same when the real parts are equal and the imaginary parts are equal. That's going to be when the two complex numbers are the same. Okay, so what I like to do for these types of problems is I like to set up an equation for the real parts, and I like to set up an equation for the imaginary parts. So what are the real parts? 2x is real because it does not have an I in it, and 10 is real because it does not have an I in it. So I take the real part from the left and right hand side and I set them equal to each other. I do the same thing with the imaginary parts. I take the imaginary part from the left side of the equal sign and I set it equal to the imaginary part from the right side of the equal sign. Then I solve. What would x have to be? 5, right? If we divide both sides by 2, then x is 5. And this is already solved for, right? Y is negative 7. No. And then I like to check my work. Check. If x is 5, I would have 2 times 5 minus 7i on the left side. Right? On the right side, I would have 10 plus, what's y? We said y was negative 7. Does that make a true statement? 10 minus 7i equals 10 minus 7i? Yes. See how it's equal on both sides? That's like how I like to check my work. Okay, once you get a solution for x and y, plug it in and see if you get a balanced equation. So you guys do one. Let's do this one. Okay, what are my real parts? From the left of my equal sign, what's real? X. And from the right hand side of my equal sign, 9. Okay. All right, imaginary parts. On the left hand side of my equal sign, what's imaginary? 3i, right? But I just used the leading coefficient. Okay, so I'm just going to use 3. And on the right hand side, what's my imaginary part? Negative y, right? I don't need to put the I there. Negative y. Okay. So I end up with x is 9. And then how would I get y by itself? Divide both sides by negative 1. Then we get that y is negative 3. Okay. So once I get my solutions, I like to check my work. If I were to plug in these values, what would I get? This would be 9 plus 3i, right, because x was 9, equals 9 minus, and what was y? Negative 3. Does that make a true statement? 9 plus 3i equals 9, plus 3i. That's true. Okay, it's balanced. See how that works? Okay.